Hey folks, this is Major Jones and Isaac Jones here to talk to you about finite state machines. And so to review really quick, right, we've had two lessons so far. First, introducing the idea of what a finite state machine was and how we draw some state diagrams. And then next we talked about how we're able to construct a circuit using these state diagrams with some combinational logic and my flip-flops and how we represent that, the state diagrams with the state table. Okay, a little quieter. So today we're going to take it full circle, and we're going to show you how we were able to take that state table and actually build a circuit to implement something. So here's our simple finite state machine we're going to talk about today. All right, we're going to build a very basic toaster. All right, so this description says that we've got a toaster. It's going to toast bread, and so it's got three inputs. I've got this little bar that I can push down to sort of start my toasting. And then while the toaster is running, it's going to turn on the latch to sort of hold the bar in place and the heater to start my toasting process. And it's going to listen for two things. If I press the cancel button, it'll automatically sort of return to this state where it's kind of waiting. But it'll also return there if the timer is expired. Okay, so here is. Oh, excuse me. All right, remember, no faces, kiddo. Just sit and watch. Okay, so here's the state diagram that I've drawn to kind of model this simple finite state machine. I've got sort of a wait state where my heating element's off. That's number 0. If I press my bar, I go to my toasted state. My heater turns on, and I'm waiting here for either the cancel button or the timer to expire before I go back to this state. Right. So just like you saw in the last lesson, right? I'm gonna write out my state table, and I did one big state table here, even though it's a little redundant for the output, just to kind of keep my space low. But it's pretty obvious that my heater is on whenever my my state bit is 1 because I'm in this state here. So this state table, given the current state and what are my inputs, bar, cancel, and timer, what should Q prime the next state be? I've filled that in here, and then I've transferred it to my K-map, and I've determined my expressions for the next state bit using my current state and my input bits. And this is kind of where we stopped last time. And so hopefully it's not a really big logical leap to sort of show you that, okay, well, in this case, my output H, right, that's here in my circuit. It takes my state bit Q. So just like we saw in that last lesson, I hold my state bit here in this D flip-flop, and it is the output that goes, the output of this D flip-flop that goes directly to the output of my finite state machine. It might be that my output bits have slightly more complex combinational logic, and so if this were like an expression, you'd see some gates in the middle here. And then Q prime is just whatever is the next bit that I want my state to be. So that's going to be the value that is put on my D flip-flop here. And so I formulate this expression that I determined using my K-map out of my logic gates. You can see my inputs and their inverses here. And I sort of wrap my current state bit back around here into my network. And this should form my finite state machine. So let's test it out. If I open up Logicsim and I start running it, I should see sort of this behavior, right? So let's turn on, all right, so here my clock's going, and I should turn this on just a little bit faster. And so I'm in state 0, and based on my state diagram, if I press my cancel button, nothing should happen. If I press the timer, this doesn't exactly make sense for my system, but nothing should happen. It's only when my bar is pressed on this on the positive going clock edge that I go to this state now where my heater's on. And if I continue holding down my bar, nothing's going to happen because my state diagram is nothing should happen when the bar is pressed when I'm in this state here. It's only when either the cancel is pressed that I go back here, or if timer expires, I go back to my default state. And so this demonstrates that our design works, that it does what we want it to do. And it was a direct application of just the expressions that I determined using my K-maps, which I built from my state table that ultimately came from my state diagram. And so over the next couple lessons, we'll see a couple of different ways to implement these finite state machines. And of course, at this point, this is something we can build in the lab if we want to. We've used D flip-flops before. You know how to use AND gates and OR gates to construct this logic. So this is kind of like one implementation of the finite state machine that we can build using just some of the chips that we've already used in our lab. All right, folks, that's all I got. We'll see you next time.